And then I'm going to now start taking you out to other places in the universe. I'm trying to link these stories a little bit, but the Dark Energy Survey is a survey primarily looking deep into space to try to get a handle on what dark energy is. And dark energy is that stuff that we don't know what it is, associated with empty space that is causing the universe to accelerate in its expansion. To look at these really faint objects, it's got this the best camera of any telescope in the world at the moment. Here's its camera. Here are the people looking in the back of it. It's a series of CCDs that are laid out here in this big panel, and the total amount of pixels in this is about 500 million pixels. Okay, so compared to your 10 megapixel camera with 10 million pixels, this has got 500 million pixels, and it can see big swaths of the sky. And so one of the things this thing is actually observing are some of these trans-Newtonian objects. It's found quite a few already. So it'll be helping more with that effort. But in this kind of last month, they had shown this one kind of object that wowed them a bit, and I just thought it was a beautiful photograph here. They weren't expecting to see this here and everything, but they just kind of were randomly mapping the sky, and this is the Comet Lovejoy that happened to fill up their whole screen here and everything like that, and their images and stuff, and it's just a gorgeous image there. So, but they weren't targeting it at all. Now, more related to the news that they kind of let out this particular month. This is actually a dwarf satellite galaxy called Leo 1. And it's, I can't remember where the image is from and everything, but these are small, fairly compact galaxies that are going around our own Milky Way galaxy. Just to put it in, well, here's how one looks out on the sky here. And so here are several other like galaxies that are satellites to our own Milky Way galaxy. Now, we live in the Milky Way galaxy, so we're looking out in different directions, and this is where we've discovered some of these objects. Now, reconstructing them in space, I don't know if we'll be able to see this here very well, but here is kind of more of a three-dimensional thing. There should be a little round grid up here and a round grid down over here. Here's the Milky Way. Here's Andromeda. The distance between those two galaxies is about 2 million light years. And here are a bunch of satellite galaxies around the Milky Way. Here's Leo 1 that I showed you a picture of. Well, anyway, the Dark Energy Survey project is turning up more of these dwarf satellite galaxies, and it's very important for us to find because they put constraints on what we think dark matter is. We really do think there should be a lot more satellite galaxies out there that we haven't discovered yet. So it is actually now adding a lot to this. It's already in this part of space here has added 8 new potential candidates for these very tenuous dwarf galaxies. Now, I'm going to show you this next image here. Here's the actual image that one takes from the Dark Energy Survey camera there. And there's a lot of stuff in there. As you go through that, you can then start saying that which of these are stars in our own galaxy and which are not in our galaxy, and you can start throwing those out and reconstruct the map that are beyond our galaxy, and this is what you get. And this is they've found about 300 stars in this very, very small dwarf galaxy around there. So it has the potential to really find more of these objects. Is very important from our cosmological models to find these things. But you can see that's a pretty difficult task to do. Now, a somewhat related thing is here's not a satellite dwarf galaxy, but we'll call blue dwarf galaxy or a compact blue dwarf galaxy. This particular galaxy is about 12 million light years away. So on that map that I showed you, the distance between Andromeda and our own Milky Way is 2 million, so this is about 6 times further away. But this is a very, very interesting object. It's a dwarf galaxy, and it's very, very blue because there's all this star formation that is occurring in this particular galaxy. And they're down in this region, which you see a composite of the Hubble Space Telescope imagery, and these things you see in red are done in the what we call the radial part of the spectrum, and they're looking at molecular carbon monoxide, actually. So it's telling you where a lot of the gas is in there. And you can see over here where these are, there's this big kind of black spot right here. So there's occulting dust right here as well. But at this core here, there are about 7,000 O stars that have formed down in this core. O stars are the largest stars that form. And there are 7,000 of them that are in here. This galaxy has a lot of dark matter in it, about a ratio of 9:1 of dark matter to visible matter, which is much more enriched than our Milky Way, at least the central parts of our Milky Way. They didn't think you could get this kind of star formation in these galaxies. And O stars only live for millions of years. So this structure here is only a few million years old. And out of those 7,000 O stars, they're going to be going supernova. They haven't seen any supernova in there yet. So this is like crazy system where you've got tons of thousands of stars that are going to start going off. I say any day now, but any million years from now. So, and how is all that star forming happening in this galaxy? They believe that material is funneling along in this direction, and it's being basically fed into this from external to the galaxy. Now, why is that material streaming along there? They didn't answer that question and everything like that, but it's a very interesting galaxy. Okay. The next story, I'm going to get way out there in space here a little bit, and this is another interesting find from the Hubble Space Telescope. We've talked in the past about something called the Frontiers field. There are 6 fields the Hubble Space Telescope is looking at that are large clusters of galaxies. So in this image, all these are galaxies. There's this huge cluster of galaxies. What Hubble's doing with this particular study, which they've got lots of time to on the telescope to do, is they're studying the cluster, the dynamics of the cluster, but the main emphasis is to study things behind the cluster that are being gravitationally lensed by the mass in this cluster. So Einstein showed that a mass warps space-time, and that warpage of space-time causes light to bend. So when you have a lot of mass, and most of the mass that's here is actually in the form of dark matter, it can bend the light from objects that are directly behind it. And so the find that they had here, which is really cool, is if you look in this core structure over here, here's the blow up of here, you see 4 dots over here. Those turned out to be all the same objects that is being lensed from behind this cluster. And those 4 objects that showed up here are all a supernova that went off in the more distant galaxy. And this is the first time that we've seen multiple images of a supernova. We've seen multiple images of like quasars and galaxies and things like that we would see, but we've never seen it where we saw a supernova actually go off. And so in this, which I forgot what, it was 2014 that they saw this, each of these points here are the same supernova, but they happen at different times. And these ones I think happen within days of one another. So you get the opportunity to watch the same supernova many, many times. And it gets better than that because what they've done is they've mapped this whole region of space here with the clusters and stuff, and they've created kind of a map of how it actually is deflecting the background light. So they actually know what galaxy this came from. And I should point out that these 4 supernovae that you see around here are not in this galaxy. That is actually a giant elliptical galaxy at the center here that is actually also in line creating an additional lensing event and making, basically if that was taken away, you'd see 1 supernova there. And now because of that additional one, you're seeing 4 because of the alignment and everything. So here is the kind of geometry of what you're seeing here. So you have a background galaxy. There's where the supernova is going off at. Here is the cluster of galaxies out in front of it, and here's the Hubble Space Telescope. And the light that comes through here is then encountering the gravitational field of the huge cluster, which is causing it to focus in this direction. It's getting an additional boost from this that's causing 4 of those images actually to be seen there. But they've mapped this cluster, and they now know that there's other paths that can happen here that one of these paths here, I think this one here, was seen in 1995. Well, we would have seen it in 1995 based on their calculations, and then this one here we'll see in another 5 to 10 years there. So they'll be watching this, and that's just based on how things are laid out here. And you can see this path is longer, so it's going to take longer for the light actually to travel along this path. So here is a movie just kind of constructing what I was just saying there. So you can see the individual paths. So the one there is the one that hit in 1995, so I was actually backwards there. And then there are 4 that were made from that path that was currently observed in 2014. And this other one that we'll see somewhere between 2016 and 2000. So here are the points on the sky there, and you can see the different observations here. So there's the 2016 there. So there's a galaxy that they probably identified, which is what you see in there. That's the same galaxy that had the supernova in there. So that's really cool. You got this predictive power that we know there's going to be a supernova. When we have bigger telescopes there, we can really be right on it when we observe that supernova. Okay, and my last story that I'm going to talk about is this kind of figuring out something that happened in 1670. Okay, in 1670, a object showed up this part of the sky. This is Cygnus the Swan. It's a constellation that's fairly easily identifiable here, and I like it because it actually does look like a swan. You see the wings that come out over here, and then over here at the tip of it, this brighter star over here is a neat one to look at in the telescope because it's a binary, and one is blue and one is yellow. So it's a pretty cool object to look at. But oops, sorry about that. The object here, I'm pressing the wrong button. This object here, like I said, was seen in 1670, was bright enough to see in the sky, and it actually reappeared a few times. And so the thought was it was always what was called a nova, not a supernova. And a nova is an event where you have a close binary system. You have a white dwarf as one of the objects, and that white dwarf is pulling material over from the companion star because it's very, very close. And eventually that material piles up on the white dwarf and ignites very, very quickly. And so the white dwarf flares up and puts out a lot of energy, and there's a kind of a chemical signature of that, and many astronomers are studying this particular event here, other novas that are going on in the Milky Way. Now, when they went and looked at that point in the sky, somewhere here in the center, and we'll zoom in on this region here, but you don't see much there, but it's a very, very faint object, and they've taken recent data here that here's the structure that they see now in that area where the nova occurred. And what they've been studying is what you see here in red here is actually from, again, radio emissions looking at, in this case, it's ALMA data, the Atacama Large Millimeter Array that sees cold gas in this area and can build up the composition of this. And anyway, it does not match what is expected from a nova. So what they now think, and it does match to, is a much rarer occurrence, and that is the collision of a couple of stars that happened at that time. Now, they didn't get into detail. I mean, I don't think there's a random collision. I think this is probably a binary system that is either perturb, or maybe a trinary that you perturbed one star and one basically ultimately coalesced with the other. And in that, you can get a bright event, brighter than the nova, but not as bright as a supernova. And so these are extremely rare. I often talk about, like, if you throw a star in one end of the galaxy, it has almost no chance of colliding with another one. That's how much empty space there is. So my guess is though they didn't talk about that, is that would the likely thing is a binary or trinary system, but you have this essentially a collision between stars, and we've never seen that. So I'm gonna leave with this movie here that shows a nice zoom in to this region of space. Do like the way the stars are flickering there. That's kind of cool. And just to see how far you have to zoom in to get to this region of space. And ESO does a wonderful job of compiling, taking all these data sets and putting them together to show these zooms. But there is that object in its field. It really shows the kind of capabilities that we have from our little Earth here and looking out into space. And so when I look at, um, images like that, which, again, this is the same image I showed before, it just makes you feel like we've got a lot of work to do. you know, there's no end to our discovery of finding those objects. There's just little nuggets that are buried out there in space. And it's a very cool story in the sense that, observations back in 1670 basically, were instrumental in kind of locating this object and then ultimately finding, what it's all about and unlocking this mystery.